Conservation of mechanical energy. In this video, the focus is mainly on mechanical energy and the principle of conservation of mechanical energy. Before working on this video, you need to know what potential energy is and the relationship between potential energy and conservative forces. If necessary, you should refer to the following video which covers this topic. Thanks for watching this video and don't forget to like, subscribe to the channel and activate the notifications. It is very important to the continuity of this channel. Before we begin the study of the principle of conservation of mechanical energy, let us recall the concept of conservative force. Conservative force depends on the initial and final position, not on the path between them, and the work done by conservative force equals the negative change in potential energy. A non-conservative force is one for which work depends on the path taken. Therefore, a non-conservative force does not result in potential energy stored. Friction is the best example of a non-conservative force. For example, sliding a book from point A to point C, C to B, requires more energy than sliding a book directly from point A to point B. The work done against friction depends on the path. A non-conservative force is generally dissipate, which means that it tends to randomly disperse the energy of bodies on which it acts. This dispersal of energy often takes the form of heat or sound, and it cannot be fully converted back to work, so it is lost or not recoverable. Gravitational force and elastic force are good examples of conservative force. Kinetic friction and air drag are good examples of non-conservative forces. The mechanical energy of a body is the sum of its potential energy and kinetic energy. In this video, we examine what happens to this mechanical energy when only conservative forces act on a body. That is, when frictional and air resistance do not act on the body. We know that the work done by a conservative force is the negative of potential energy change. We also know the work done by the net force on a body equals the change in the body's kinetic energy. We can combine these equations. Rearranging the equation, we arrive at the following very important result. This result is called the principle of conservation of mechanical energy. In words, this equation says the total mechanical energy does not change. Its final value is the same as its initial value. When a physical quantity is conserved, the numeric value of the quantity remains the same throughout the physical process, although the form of the quantity may change in some way. Now you can see where conservative forces got their name. Let's see how the principle of conservation of mechanical energy works. Galileo takes a 5 kilograms cannonball to the top of the Tower of Pisa for one of his experiments. The tower is 56 meters high. Air resistance is ignored. Calculate the speed of the cannonball when it reaches ground level and the speed of the cannonball when it reaches 20 meters above the ground level. Let subscript 1 correspond to the ground level. Let subscript 2 correspond to the state at 20 meters above the ground level. And finally, let subscript 3 correspond to the state at 56 meters above the ground level. As the air resistance is negligible, we use the principle of conservation of mechanical energy. The mechanical energy at instant 1 is the same as the mechanical energy at instant 3. We write the energy conservation equation and supply the proper terms. We cancel the mass m and replace V3 with 0 H1 with 0, H3 with 56, and solve for V1. To find the speed at 20 meters above to the ground level, we will do the same as we did before. Pay attention. A block of 2 kilograms is pushed against a spring, compressing it a distance at 0.5 meters. Calculate the maximum speed that the block acquires when the spring is released. The block will travel on a frictionless surface. An undeformed spring has no potential energy stored in it. The force needed to compress the spring does work against the spring force. Because the spring force is conservative, this work is stored as potential energy in the spring. When it is released, it transforms elastic potential energy into kinetic energy in the same way as in the previous example with gravitational potential energy and kinetic energy. Since there is no friction, we use the principle of conservation of mechanical energy. Set the initial mechanical energy equal to the final mechanical energy and solve for V. The subscript I refers to the initial position and the subscript F refers to the final position. The block starts at rest at the initial position, where the spring is compressed by a distance 0.5 meters, and leaves the spring at the final position, where the spring is at its equilibrium position. In this point, x equals 0. When the block leaves the spring moving to the right, its speed is 5 meters per second. A body of mass 4 kilograms with initial speed 5 meters per second begins to move up an incline as shown below. The body will be momentarily brought to rest after colliding with a spring of elastic constant 180 newtons per meter. The body stops a vertical distance 0.8 meters above its initial position. Determine the amount by which the spring has been compressed. There are no frictional forces. So we apply the principle of conservation of mechanical energy. The subscripts I and F represent the initial and final states. In the initial state, we know the speed of the body. The height is 0 and the spring is not compressed. Therefore, there is no potential energy stored. In the final state, the body is momentarily at rest against the compressed spring at its highest point on the incline. Therefore, at this point, the body has potential gravitational energy and elastic potential energy, but the kinetic energy is 0.